So it's fantastic to be here. That was a very inspiring talk, and so today I'm going to talk about Ascent in competitive arenas because a lot of the success of the background is a competitive arena. So what do I mean by that? So essentially a system where there's finite number of opportunities. So in some sense, not everybody can be a winner. But I think it's really important to really understand and reflect on what we just learned in the last talk, that you can't discount the role of ambition in some of these superstar scientists. So maybe it's... So I'm going to start out by showing some plots of just three individuals that a lot of people in the room are familiar with. So that's Mozart, Gene Stanley, and Babe Ruth. So these are three individuals who I think we can check the box of ambition. But the thing that we might not necessarily find to be common between these people is the patterns of growth in their career. So if we had just kind of a null model of kind of output within the career, maybe every individual is endowed with some sort of constant rate in which they're producing, say at an annual basis. But in fact, what we're going to find is that these careers are growing throughout the career. So this is really actually in conflict with kind of economic arguments that you might make, in the sense that if you know that basically you're going to die someday, the incentives to invest in future kind of kickbacks decreases as you get older and older. And so it's just predicted that your productivity is going to kind of saturate, or if not decline, as you get older. So I shouldn't have made such a pickiness about the size. So what we're going to see is basically something like this.
Keep going, it's good.
On the x-axis, we have career age, so that's just basically the number of years since the first output. On the y-axis, we're going to have the cumulative number of outputs. So that's basically, the total number of papers published in year 10 of the career, or in the case of Mozart, the total number of compositions, say, by year 10. And if you look at the data for Mozart, he was actually quite a wily 8-year-old.
Do you have a USB key by any chance?
Sure. What happened?
It's your laptop.
Oh,
It's
yeah.
not being responsive.
Yeah.
Oh.
So let me change your computer.
Okay.
Oh, keep going.
Here. I already have it.
Hey, I'm interested in the outlier.
That's like splash of growth right there.
So we could take questions actually if you want.
What more can I say? So basically, the model that you would expect is that you have this proportional growth with time. So just the total number of outputs is kind of grows proportional to time. But what we're going to see, in fact, is that the cumulative number of outputs grows superlinearly. So we can assign kind of an exponent to this growth quantity. And for all these three individuals, it's actually superlinear, or greater than 1. So in the slide after that, I'm going to show how we've aggregated over top scientists in the domain of physics, cell biology, and mathematics. So these are the same actual scientists that we were talking about with Santo earlier, looking at these kind of predictive models. And so the point is, when you aggregate properly over these individual careers, you find that, again, there's basically this characteristic property of star careers in which they keep on growing. And so in science, we can really come back to the idea that it's a collaborative endeavor by which we gain opportunities by collaborating, very much in the sense of finding new knowledge bases and bridging between different knowledge bases. So it's not so surprising that you see this growth that can be sustained actually for quite a long time in these superstar careers. Thank you.
Everyone see the curve he was talking about? Beautiful, powerful, it's like rainbow. You want to use this PDF? Yeah.
coming. Yeah.
Just full screen that.
All right.
Just Command L. Yeah, yeah.
Thank you.
3 minutes left.
All right. So here's the curve. Here's Mozart at age 8. You know, he basically was quite an ambitious individual. You know, he learned quite young that, you know, he had this talent, and he basically pursued it. Here's Babe Ruth. This is just a measure of offensive output. It grows with, you know, some sort of scaling exponent that's greater than 1. And then you have Gene Stanley, like I said, whose ambition is, and role as a leader has allowed for this growth that seems to be, you know, not stopping. Here's like what I said, if we aggregate, we see these statistical patterns both for just the publication rates and also for citation of these scientists. You know, basically we get exponents that are greater than 1, which really correspond to this, you know, risk get rich, or this cumulative advantage whereby careers become attractors of new opportunities rather than pursuers. So, and then I started to talk about how it's really the socially embedded aspects of science that make it really complex. So obviously, you know, for any individual, we can project them onto a system of collaborators or enlarge the invisible college. And at any given point in time, they're really interacting in very particular ways. And so there's, you know, various aspects of this interaction. So collaboration is kind of an attractive force. Competition for priority and these limited resources is a repulsive kind of idea. And knowledge is the kind of the glue that holds the system together in some sense. So let me just start by illustrating 3 examples of scientists who had completely kind of diverse strategies as far as collaboration. So for here you have Michael Brown and Joseph Goldstein. They won the Nobel Prize in 1985 for their research on cholesterol. And basically I would like to call them like a Watson Crick or a Batman Robin type duo, in the sense that they published 95% of their roughly 450 papers together. So that's, you know, a good team, basically. But at the same time, within the cohort of basically the top 100 cell biologists of recent times, you have Marilyn Kozak, who decided to take a completely different strategy as far as her career, and she published 84% of her papers as a solo author. So this is quite surprising when you think that she's an experimentalist who's doing basically every aspect, grant writing, you know, she's in the wet lab, et cetera, et cetera. And so now when you add the kind of dimension of the citation networks, which is the quality aspect of the outputs, you realize quite quickly that this is a complex system in the sense that, you know, you have reputation signaling going back and forth. So the reputation of a paper can impact the reputation of a scientist and vice versa. There's behavioral components. These are humans. I mean, we're human beings in the sense that we have ability to see the future and to make decisions. And so it's really quite a fun system to play around with. And so when I talk about competitive arena, if you walk down the street in Boston, you'll probably get one of these two types of answers. So a lot of people in you know, Mass Ave will tell you that these are the arenas that they're basically shooting for. Moreover, by Kenmore Square, you have maybe, you know, David Ortiz walking around, and this is basically his arena. And so this is just the data that I'm going to quickly talk about. So we're going to look at careers within these arenas. And so this is our disambiguation strategy. We basically analyze the subset of rare surnames within these journals to get roughly a data set that we're highly confident was disambiguated. And so I'm going to focus here on the Nature PNES science arena. And so there's basically 2 measures that we can kind of get a first understanding of these arenas and how there's a disparity actually between the one-hit wonders and the iron horses. So basically, for instance, if you look at the longevity, so the number of years that they've been publishing in one of these 3 journals, you see that basically 67% of the scientists publish, you know, over a duration of 1 year. 23% published for more than 5 years, and around 14% published for more than 10 years. So that gives you kind of an idea of the fact that many individuals are popping in and out, kind of like you know, from the minor leagues in some sense. And then there's also some long-standing kind of pillar scientists who basically publish for their entire lives. And again, you kind of see the the analogous picture, if you look at the total number of publications, it roughly follows Lotka's law from 100 years ago or so. Okay, so let's look at a possible mechanism that could be responsible for this extremely right skewed distribution. So consider just basically the schematic of a career. Basically, you have achievements that occur throughout the career. In this sense, it's publishing in these top arena. And so the question that we might ask is, what is the characteristic waiting time, tau of n, between an author's nth paper and his next paper, his or her next paper? Okay, so if we just look at what the data tells us, so this is looking at for careers that are longevity more than 5 years and more than 10 papers, we see basically a significant decrease in the waiting time as they continue to publish in these top journals. And so for example, by the 10th paper, the waiting time, which was initially roughly 3 to 4 years between the first and second paper, roughly decreases by a factor of 2. So this is kind of the cumulative advantage, which is a social mechanism based on reputation that allows for careers to really start to grow. And so we've constructed a model in which basically you have a kind of a hopping process that models the progress of a career. And so what we did was we compared the predictions of the model with these two kind of competitive arenas. So we looked at professional sports and academia. And if you look at the longevity distribution, so on the x-axis are basic measures of kind of career length. Here it's defined in number of years for publishing in top journals. And here for baseball, for example, the number of at-bats. So here we looked at both Korea and the USA. And remarkably, so I'll tell the story in the terms of baseball. So, it's roughly a complete labor force that's been, 130 years or more and 15,000 careers that we can analyze. And so when we do this, we find that there's quite a remarkable frequency of one-hit wonders. So 3% of all fielders, so those non-pitchers, finish their career with one at-bat. And, similarly, 3% of all pitchers finish their career with less than one inning pitched. So these are a large fraction of the labor force that probably you've never heard of, but they're definitely there. Conversely, if you look at the tails, so there's kind of this truncation, which really reflects the finite life scale. But it's populated by very significant individuals, such as Lou Gehrig, who was had the moniker of the Iron Horse, in the sense that he played in this is a statistical anomaly. He played in 2,130 consecutive games without missing one. So that's pretty impressive. And sadly, his career and life was stunted by the neuromuscular disease ALS, also known as Lou Gehrig's. So probably going to skip this part. So we can model kind of competition using agent-based models. In this paper, we looked at the role of prior achievements appraisal. So you can say that the capture rate of opportunities is proportional to some appraisal over the prior history of achievements, except that there's an exponential discount factor, which means that in some sense you can discount the achievements from early in the career rather than say yesterday. And we can study the role of appraisal timescales, which are related to the tenure system versus a short-term contract system. And the basic kind of results of this simple model is to understand the role of short-term appraisal systems and how they might be actually causing higher risk scenarios in science. So for instance, we found that the short-term appraisal can amplify the effects of competition and uncertainty. They effectively discount the cumulative achievements, and they may reduce incentives for individuals to invest in human and social capital accumulation. That is, if you have short-term contract, then probably you're going to need to store, a paper in your back pocket that you can publish just in case, basically, things get kind of the uncertainty horizon kind of approaches. So this is kind of like the institutional trends that are making this science of science really a interesting and very relevant topic these days. I mean, if you look at how science evolved and the incentive systems, we're entering a new domain that has completely new problems. The organizational shifts in the business structure of universities, which are becoming more like companies. There's more of emphasis on bottom economic bottom lines. This is related to the contract lengths and the bottleneck in the number of tenure track positions per graduate student, et cetera, et cetera. And also, there's new emerging online competitive arenas, and whereby really the online presence is becoming more and more important. So I must have been talking really fast. So and so then basically there's the increasing team size effect, which Utsi is very led the science into this research area in this context that's the team size effect is really causing us questions that we must ask, which are how to fairly distribute credit in a system dominated by teams. And so this feature basically requires us to rethink how we distribute prizes, how we distribute recognition of precedence, and also the role of money in science. And so if we look at the inflation problem, so if we just look at the number of papers published in these 3 high-impact journals, there's roughly a 0.4% increase growth rate over this period. However, if we look at the average number of co-authors per paper, it's significantly more. But the times are changing, and so now we have a new kind of ecosystem of publication output that is really changing the relative measures for publications. So if you look at PLOS One's monthly growth rate, it's pretty astounding. 4.8% growth over basically the period of the journal. And so just in the period 2010 to 2011, there was a factor of 2 growth in the number of publications. So this is really begging the question, who's reading and refereeing all these papers, and what does it mean for science? Okay, so I'll just really quickly finish, since we're a baseball town, on how these issues of success impact inflation can be considered in other systems. So if you look at the home run ability rate, say per opportunity, you can see that there's been a drastic increase over the entire history of the game. And in fact, you can tie some of the trends to institutional kind of implementation. So raising of the mound in '62, lowering of the mound in 1969. And so, but in economics, this idea of inflation, they deal with it quite simply. They basically just renormalize to some sort of baseline year. So there's a reason why if you look at this, the price of this candy bar, it only says 5 cents, because basically there's been an inflation in the purchasing price power, which we can deal with. So applying the same kind of method, we can also renormalize and account for the socio-technological factors that underlie achievement in professional sports. And so by applying this method that we developed, you can kind of make a statistical baseline which allows you to compare achievements across time. And so I'll probably just finish with this slide. But if you're into barstool debates, then you can check out these papers in which we applied this method and re-ranked the all-time achievements for basically all the statistical categories that you can find on the back of baseball cards and basketball cards. And in this case, basically, we're looking at cumulative number of home runs. And so you see that Barry Bonds, if you account for the fact that these socio-technological factors have increased the home run ability rate, then you can renormalize, and you see that Babe Ruth, relative to his peers, had an astounding cumulative impact as far as home runs. And also some other names kind of pop out of nowhere from our distant past. And it's really comes down to the preservation of really our historical baseball preservation. All right, so I'll just finish there with this slide. So thank you very much.
Nazım.
No, I mean, I think it's really something that should be done sooner than later because, I mean, it's really a basic, the number of citations that can be allotted has to be in somewhat proportion to the number of papers published. And so, the value of a citation is not the same comparing today versus, even 10 years ago.
Yes, Cesar.
I sort of looked a little bit at that science, the number of papers that they publish a year is fixed, and the number of people that is participating in science is increasing. So on one side, in the inflation, basically the value of the citation goes down, but on the other side, did you look at whether in those journals becoming a new entrant is becoming increasingly more difficult, and that basically they become fields, for incumbents?
No, I mean, if the growth rate of co-authorships per paper is larger, then it's in fact becoming easier, no? To become.
Because you're entering, let's say, I'm entering because I'm entering with someone that is.
Oh, you said incumbent. Sorry, I heard entrant. No, that's obviously a feature that has to be kind of incorporated and kind of teased out as far as creating kind of all-time lists. And that's basically what we tried to, at least in a primitive sense, do for professional sports, since it's obviously a lot easier. But yeah, it's a complex system, so a lot has to be done.
One thing that always amazes me, so I love in general, the analogies with sport, but yesterday we spent half of the evening talking about tennis and what tennis can sort of tell us about excellence and success and impact and that sort of thing. So the problem I have with a sport like baseball, right, and comparing that to science and how productive people are, number of papers, number of citations, isn't it that, since, as you point out at the end, scientists increasingly work as teams, and the relative contribution of everybody in each one of these teams is very, very different. It's as if you said, for an unknown player who happened to be part of the Red Sox, or when they were good, or whatever other team, I don't know baseball very well, and sort of basically told a story about how great they are because they were sitting on the bench most of the evenings that the team. So do you see what I'm trying to say? So you take a very powerful example with individuals, like
Right.
Lou Gehrig or something like that, and then we try to understand the science part of it, but that's increasingly a team aspect. So, for example, Kozak, I love her work. I remember reading it in 1980. She is like Lou Gehrig, right? She's doing it. So I'm not sure that I understand how we can learn from between the two different fields if we use them so differently. Can you
Yeah.
comment on that a little bit?
No, certainly I think you raised the point that understanding the role of basically the productivity spillovers from your team
Right.
is really difficult to make that comparison. Mainly saying, is science becoming more like a professional sport in the context of the risk scenarios for the individual?
Yes.
So if basically in sports we have really the possibility for really short contracts, but there's also tied to that to make the incentive system work really big pay scales. So we'll kind of see in the era of big science and big money if this shifts in that direction. So.
Interesting. Anything else? Oh, yeah, please, Martin. Yes.
When you start to look at professional sports, what you're doing is you're truncating the distribution to the very, very top.
That's also true.
How do you make a comparison? I have no idea myself, but how would you make a comparison between something like that, where you're looking at the super right tail, with something like science, where it takes everyone?
Well, I mean, I was looking at the top journals, which, yeah, you make it look easy.
It's just, getting to Russell's question about how you might normalize some of this stuff, the science and other things, it's to make, good relative comparisons, it's pretty tricky.
Yeah, absolutely.
Agreed. Again, thank you. That was great.